Hello, my name is Junghee. I'm from KAIST. Today, I talk about FloSIS, a high-speed network flow capture and retrieval system. Network monitoring performs an essential function in network management, such as network provisioning and attack forensics. For effective network provisioning, we need to have accurate statistics of network traffic. We also need deep flow inspection to check if important data is leaking, and sometimes to reconstruct the crime. Besides, real-time network monitoring plays a critical role in software-defined networking. Typically, a network monitoring system captures and dumps the packets to disk for layer analysis. However, for the flow-level network monitoring and analysis, we need to reconstruct flows from packets. TCP dump and Wiresharks are well-known packet capture and analysis tools. They provide detailed packet analysis, but they exhibit poor performance in a high-speed network. And 2disk is a multi-gigabit packet recorder with support for indexing for fast retrieval. This packet-based system captures arriving packets and dumps them to hard disk in the order of arrival. Unfortunately, it is very inefficient to retrieve all packets in a flow, since they need to read every packet from a disk to see if the packet belongs to the flow. Indexing helps this situation a little bit, but it's still very slow because it requires lots of disk accesses since the packets are spread across the disk. To improve inefficient per packet retrieval, we design a flow-based capture system. It writes and reads the packets in the same flow at one location. It classifies the packet according to the flow information and writes the packets in the same flow at the contiguous disk space. It makes an index for each flow rather than each packet, and so the amount of index is much smaller than that of per packet index. For retrieval, the flow index tells where the flow stores in the disk. This allows reading the entire packets in the flow at one disk seek. In addition, we can think about real-time flow contents reassembly. It restores flow contents from packet payload and write the reassembled content to disk instead of packet. By doing this, we can see the contents without extra reassembly process. This allows us to improve storage efficiency by deduplicating the flow contents. So in this talk, we argued that flow-level monitoring is much more beneficial than packet-level monitoring, and we need a flow-based capture and retrieval system for high-speed network. However, there are many technical challenges in developing a flow-based capture system. First, we need to reconstruct flows in real time. We may need to handle a large number of concurrent flows, which cause large processing and memory overhead. However, we should avoid packet drops as much as possible for accurate monitoring. Second, we need an efficient design for flow-aware disk access and indexing. We target for multi-10 Gbps environment, which is very challenging since poor system performance would produce a large number of packet drops. Finally, in a high-speed network, even a single 10 Gbps link can deliver more than 100 terabytes of data in a single day. So what this means is that the flow retrieval can take many hours if we don't use indexing. Moreover, small storage space could significantly limit the monitoring period. In this work, we have developed FloSIS, a high-speed flow capture and retrieval system, which benefits from pipeline parallel processing architecture. For fast flow retrieval, FloSIS minimizes disk accesses by using a two-stage flow-level indexing structure. To achieve high throughput without any packet drop, it also limits the processing latencies. Finally, FloSIS implements flow content deduplication that removes redundancy in hard disk and improves the storage efficiency. As a result, FloSIS enjoys 36 Gbps of peak performance for flow capture. We confirm that FloSIS finishes a flow retrieval about 5 times faster than a state-of-the-art packet retrieval system. In addition, our flow contents deduplication saves 34.5% of storage space in the test with real LT trace over large ISP in South Korea. In the following slides, I'll talk about our contributions in more detail. For the high-speed performance and scalability, we designed a parallel processing architecture. FloSIS consists of multiple engines, while each engine is independent of each other. A user can configure the number of engines easily according to the hardware specification. FloSIS uses packet shaders network I/O library called PSIO. It supports parallel packet capture by multiple CPU cores. It uses symmetric RSS hashing to deliver the packets in the same flow to the same CPU core. Each engine on each CPU core reads the packet in the RxQ of PSIO. It looks up the flow table to find relevant flows for each packet and update the flow. It reassembles the flow contents and calculates the Shao hash of the flow contents for deduplication. When a flow is finished, the engine thread creates an index for the flow and copies the flow data to a buffer to write it to the disk. FloSIS writes many flows to multiple hard disks simultaneously to achieve high disk writing throughput. Each engine of FloSIS is pipelined to minimize the contention by competing operations. An engine consists of 3 types of threads. The first one is engine thread, which processes the most of the operations of an engine. A writing thread writes buffered flow data to its own hard disk. An engine thread can have multiple writing threads depending on the configuration, considering the total number of hard disks. An engine also has indexing threads that performs index sorting, flow retrieval, and index writing to solid-state drive. I'll talk about the details of the operations later. We adopt this pipeline architecture to avoid the contention by I/O operations. Co-locating packet reading and disk I/O on the same thread could significantly delay each other. So we separate these operations to the different threads. We also spread other CPU-intensive operations such as Shao hashing, index sorting, and flow retrieval. To avoid the thread scheduling issue, we allocate different CPU cores to the engine thread and the indexing threads. We designed a 2-stage flow-level indexing architecture for fast retrieval. FloSIS stores many flows in a file which has a pixel size like 1 GB. It creates a set of indexes for each file. The first stage is the file indexing that consists of 2 timestamps and 4 bloom filters for IP addresses and port numbers. The first timestamp is the start time of the earliest flow in the file, and the other timestamp is the end time of the latest flow in the file. The second stage is flow indexing that has 4 sorted arrays for IP addresses and port numbers. Let me explain how to create these indexes and how to search a specific flow with an example. For each flow, we have flow metadata. Each flow metadata has source and destination IP addresses and port numbers, and start and end time, and disk location and length of the flow data in hard disk. For the flow metadata, we have 4 sorted arrays for IP addresses and port numbers. For example, let's see a sorted array for source IP addresses. This array includes all source IP addresses of the flows in the file, and is sorted in the ascending order. Each slot has a source IP addresses and a pointer to the corresponding flow data. And the bits in the bloom filter are marked according to the source IP addresses of the flows in the file. Then let's see how to use these indexes to retrieve all flow. Here is an example flow retrieval query with a specific time range and a source IP address. A user can give a singleton or a range of values, and FloSIS can handle both of them efficiently. In the first stage, FloSIS filters the file by timestamps and bloom filters to see whether the target flows reside in this file. Besides, since the timestamp and the bloom filters are in the memory, FloSIS finishes this step very quickly. In the next stage, it reads the sorted arrays and flow metadata on the file from an SSD and runs binary search and on the sorted array to find the wanted flow. After that, it accesses the flow metadata using the pointer in the sorted array. Then it reads the flow data from a hard disk using the disk location and length in the flow metadata. By doing this, we try to minimize the number of disk accesses and improve the performance. To achieve high performance without packet drop, we need to remove unpredictable processing delay. If reading packet from NIC is delayed too much, then the buffer in the NIC could become full, so there is no more space to buffer arriving packets temporarily. This causes sudden packet drop. This unpredictable delay can be caused by several issues. The first one is thread scheduling. To avoid the random delay from scheduling, we pin each thread to a CPU core. It also improves CPU cache utilization. The second one is unpredictable disk I/O delay. We avoid latencies from file system cache by using direct I/O with a large buffer and pre-allocating disk blocks for sequential disk access. The third one is runtime dynamic memory management overhead. We overcome this problem by pre-allocating memory chunks at initialization. In addition, our careful implementation helps minimize latency fluctuation and we achieve high zero drop performance. The last contribution is flow content deduplication to improve the storage efficiency. I'll describe how FloSIS buffers and write TCP flows for deduplication. Let's think that the blue packets are upstream request packets and the purple packets are the downstream response packets. When the packet arrives, FloSIS parses each packet into packet header and payload. It then buffers packet headers in the order of arrival for later per packet analysis. It reassembles the upstream and downstream contents according to TCP sequence numbers. During that, it calculates the Shao-Nash value for each content. At the end of the flow, it writes the flow to a hard disk like this. It writes the packet headers and the upstream and downstream contents are written in the next. In front of the flow data, there is a metadata that points each part of the flow data. Then let's think about another flow that requests the same contents as the response. The flow contents are reassembled in the same way. And at the end of flow, FloSIS checks the Shao-Nash value and it realizes that downstream contents are duplicated. First, it writes only the packet headers and upstream contents. The metadata points the previous contents on another flow as its downstream contents. In this way, we can remove duplicated contents data from hard disk. From now on, we'll evaluate the performance of FloSIS. First, I'll present how fast FloSIS is for flow capture and retrieval. After that, I'll talk about the storage saving by our flow content deduplication. We build FloSIS on a server machine with 16 CPU cores, 4 10G NIC ports, 128 GB of main memory, 24 3 TB of hard disk, and 2 SSDs. We use two types of workloads for evaluation. The first one is synthetic workload. It is 40 Gbps of random packets having specific size. The other one is real LTE backward trace from a large ISP in South Korea. We replay the traffic for the evaluation. This graph shows the performance of packet capture and disk dumping of FloSIS. We compare the performance with those of TCP dump and N2Disk 10G. N2Disk 10G is a high-speed version of N2Disk for multiple 10 Gbps of network traffic recording. For TCP dump, we test both original and the one with NetMap support. NetMap is a well-known high-speed network I/O library. We check the performance with several input traffic with different packet size. FloSIS and N2Disk 10G shows high performance, which is close to the hardware limit. With 24 hard disks, we can achieve about 36 Gbps of sequential disk writing throughput at maximum. However, TCP dump shows poor performance even if it uses NetMap because TCP dump itself is not optimized for the multi-core environment. We also check the peak and zero drop performance of FloSIS and N2Disk 10G with real LTE trace replay. For fair comparison, We turn off deduplication that requires heavy shadow hashing. We check the performance of entity10G with and without indexing. For the zero-dollar performance, we measure the maximum performance that each program can process traffic without any packet drop by varying the replay speed. The peak performance of both FloSIS and Entity 10G are almost equal to the hardware limit. However, the peak zero-dollar performance of FloSIS is near 30 Gbps, while Entity 10G shows about 20 Gbps. We do not know the exact reason of why Entity 10G shows a poor performance since we don't have the source code. But it's the best performance with several tests with different configurations. Anyway, we think that our optimization that removes unpredictable latency really helps in achieving high zero-dollar performance. Next, I'd like to compare the flow retrieval times. We dump our real trace and search for the flows by querying 10 randomly selected source IP addresses. We compare the elapsed times with Entity 10G's packet level indexing and retrieval. As you can see, FloSIS achieves the flow retrieves the flows about 2 to the 5 times faster than Entity 10G. Moreover, the difference becomes larger as the number of flows in the retrieval result increases. This is because as the number of flows increases, Entity 10G suffers from much higher number of disk accesses. In contrast, FloSIS significantly benefits from flow level indexing. Finally, we check the storage saving by our flow contents deduplication. We replay our real trace and check the amount of storage saving. We also measure the memory requirements to maintain a lookup table holding the previous contents in the disks. We check the deduplication rate that is calculated by the storage saving over the total volume. For example, if we need 80 gigabytes of storage space to write 100 gigabytes of data, then the deduplication rate is 20%. We check the deduplication rate with various lookup table sizes. As you can see, the deduplication rate increases as the lookup table size gets larger. However, we confirm that the table size larger than 256 megabytes does not increase the deduplication rate, since it reaches the maximum deduplication rate of the original traffic. Anyway, it is important to see that we can save a large portion of storage space even with a relatively small amount of memory consumption. In our case, we save 34.5% of storage space with only 256 megabytes of memory. Because of heavy shadow hashing for the deduplication, the zero-dollar performance is now reduced to 15 Gbps, but it's still high enough to cover a single 10 Gbps link, which will be very helpful for increasing the monitoring period. Let me summarize my presentation. We are motivated by the actual needs and benefits of flow monitoring system, and we develop FloSIS, a highly scalable flow capture, indexing, and retrieval system. It has a pipeline parallel processing architecture and a two-stage flow level indexing for fast flow retrieval. It also supports flow content deduplication. As a result, we achieved about 36 and 30 Gbps of peak and zero-dollar performance, respectively. We confirmed that our flow retrieval is much efficient than packet retrieval. Finally, our flow content deduplication can save 34.5% of storage space only with 256 megabytes of additional memory consumption. Thank you very much. Is there any question?
I had a question about your deduplication. Could you talk about the traffic mix? Was that on your live trace or your
So we capture the traffic from the backhaul link on ISP in South Korea, and we replay them.
My intuition is that there's quite a few types of traffic that deduplication is no win for, things like SSL and video. And do you have a sense of like what the traffic mix was that led to what looks like a relatively...
Actually, watching the inside of the traffic itself is illegal, so I didn't check it in that depth, but most of the traffic was the HTTP traffic, and it was about 75%. And I didn't mention about HTTP here, but we also we also parse the HTTP header and response bodies, and we calculate the Shaonesh value for the response bodies. So we check the redundancy in HTTP responses, and then if there is a duplicated HTTP response, then we didn't write the duplicated one.
It seems like as the web is moving towards SSL everywhere, this becomes sort of hard.
If it's encrypted, then the DDoS will not work well. But encrypting everything is, I think, not that critical, because people want to make everything encrypted, but I think it will take quite a long time, I think. But actually, if every traffic is encrypted, then the DDoS will not. I think it's a bit hard to save a large portion of storage space.
All right, thank you.
Hi, I'm the author of N2Disk. I would like to comment some of your statements.
Yeah, I like this program.
Okay, first of all, thanks for using our software. It is nice to see that it has inspired some of your work. Talking about the performance, okay, yeah. I see that there are two conceptual differences between what I've done and what you have done. The main issue with N2Disk is that we cannot shuffle packet at all. So what people want to see an image of what is passing on the network. Shuffling packets or dividing them in flows is prohibited, because at the end you will end up saving to disk something that is not the same as you have seen on the network. So if you look at this picture, you see the throughput is 20G. The throughput is 20G because you have used 4 network interfaces, and you're trying to merge the traffic from those ports. And each core, because we have to respect the sequentiality of the packet, is not able to do this merging for more than 20 gigabit per second. So those data are actually good. So in order to do the same as you have done, you have to run 2 instances, each doing 20G, similar to what you're doing, no shuffling packet per interfaces, so that we have coherent timestamps. And then during extraction, we reorder the packets. Another comment I want to make is that your indexing is very smart. It's a very smart idea. But again, it goes against our principle, because we cannot shuffle packets. And also another thing I would like to comment is the following. When we write traffic at 10 gigabit, okay, this is even more true if you're running at 40. So each file per second is 1.25 gigabyte, okay? So you're saving 1.25 gigabyte per 10G interface to disk. In this second, the number of flows that you have is very huge, okay? Yeah, right. So if I've read your paper, you have said that the index is 0.25% of your file. So it looks to me that you have run experiments with a very small number of flows, that this does not happen in reality, especially if you have this type of traffic. So my conclusion is the following. Your work is definitely a step ahead, but I think you should position it in a way differently. So not just look at those numbers, because there is a justification for those numbers. Actually, I would be surprised if we will do 40G, because then there is something different. This is all. Thank you.
Thank you very much.
Hi, Daniel Waddington from Samsung. You use the packet shader network stack. And their results, I just briefly looked at it, sort of indicate that irrespective of packet size, you sort of get this great throughput. Did you actually do some experiments to look at your throughput for small packets?
Pardon?
So did you do some experiments to vary the packet sizes and then see the throughput of the system? Yeah,
actually that is the graph. So I tested I checked the performance with various size of packets. So from 64 to 150, 5014 bytes.
Okay.
So it shows high performance with the small size of packets.
Yeah, so it does change. Does it? Okay, it's about the same. Okay,
yeah.
Thanks.
Thank you.
Let's thank the speaker again.